All right. Well, good afternoon, everybody. I see we have a pretty complete class again. That's very good. So we'll do some class logistics in a little bit, but like taking roll. There was a homework set due today at 1, but since I see some people didn't realize it, or it was not clear exactly where it was, I'm going to extend that until midnight tonight. But that's the last time that I postponed the homework. You know, it's a freebie for the freebie for the first one, but afterwards, no. So last class before the weekend, we talked about Coulomb's force law, and we talked about how if you have two charged objects and you bring them closer, they start to either repel or attract, depending on whether their charges are like or opposite. And in the case of electrostatic, opposites attract and likes repel. And we then use the principle of superposition to show that if you have some configuration of charges that if you want to know what the net Coulomb force is on one of those charges, you can just choose pairs, treat them individually, as if they're the only charged objects in the rest of the universe, figure out what their Coulomb force is, and then figure out what that force is, and then do that for all pairs. And then in the end, that's your that's your net force. So the thing we'll do today is we'll try to take the Coulomb force apart, because it ends up being much easier to first talk about what a single charge does to the universe around it, and then afterwards figure out, okay, now if I place another charge close to that other charge, what happens? It makes the math way easier, but we need some concepts in the middle. So the first we'll do is we'll figure out what that concept is. The second thing we'll do is we'll have to do some tricky math, and I'm going to warn you, the math in probably the second part of the class today is going to be quite tricky. So we'll have to go from discrete charge distributions to continuous charge distributions. And the setup for that is something that most of the students that take this class in the past have struggled with. They all figure out how to do it later, but it does take some time. And we'll try to go slow, but that's something that you'll have to kind of sink your teeth in and come to terms with, because there's no way around this. You'll have to figure out how to do this. So with that being said, let me pause the recording, and then let me see if there is any questions. All right, here we go. So like I was saying, we used Coulomb's force law. We would work with some configuration of charges. We would always start with the Coulomb force law that says, if you've got two charged objects, then there's a Coulomb force that acts in a direction that is joining the two centers of those two charged objects. It goes like 1/r². This k is around 9 times 10 to the 9, and then depending on what that charge product does in terms of sign, it determines whether it's an attractive or a repulsive interaction. And then we use that for a rather straightforward one-dimensional example. We'll say, okay, so if we have one charge here in the middle between two other charges, and we want to know what this charge is, what the force is that is acting on this charged object, we can just say, okay, the force on that object that we called number 2 is going to be the sum of the contribution due to number 1 and the contribution due to number 3. And then all we're doing is we're just translating Coulomb's force law, and I used a ridiculously simple situation. I set everything to 1 meter because it makes life a lot easier. But then if you want to have a situation where the charges are not exactly the same, you can actually factor out that Q2 and figure out what Q1 and Q3 are doing, and then afterwards, when you figure out what the sign of this term in parentheses is, all you need to do is multiply it by Q2, and then you get your net force. And then we did a similar configuration, except we did this in 2D. So same basic setup, right? So superposition, write out the equations. The hard part here was figuring out what these vectors were. But then in the end, we got an expression that looked like this. We had some k times q1. Q1 is the charge of that object that we wanted to know the force on. And then we had a term in parentheses that only depended on all the other charges in the surrounding. So the question is it an accident that you can always factor out this charge? And of course, the answer is no. So let me show you how that works. So you would like to know the force on some charged object, and I'm going to call this little q. So that's the thing that we would like to know the force on. And I'm going to draw a little q. So little q sits here, and we would like to know the force on this object. Now I have, charge here, charge here, charge here, charge here, q2, q1, doesn't really matter, 3, 4. What I will do is I will say, okay, the force on this charged object F is the force on that little q due to charged object number 1, plus the force on little q due to charged object number 2, etc., etc., etc. All right, so this is where the drawing begins. So now what we would have to do is we would have to write this out. So we would have to write k q q1 over r q1 squared r q1 plus, and then we would have a whole bunch of terms. We'd have 4. The last one looks like this, q4 r little q4 squared r q4. So this is the general recipe for doing this for an arbitrary number of charges, right? We just need to enumerate the pairs and figure out, okay, once we have the pairs, the final force is going to be the product of that little q with the geometrical configuration of all. So in other words, if I want to write this instead of this dot dot notation, I'm going to use a summation notation. I'm going to write this, and I'm going to sum over n charges, and I will need a k, I will need a q, I will need a q, right? So in other words, we're going to go I is 0 to n. This is the charge under consideration, r q I squared r q I. So I didn't really do anything. I just wrote it. In a little bit more general manner. It still has that same form of the Coulomb force law, except now we're just adding the contributions of all the pairs. Now, here's the thing I wanted you to pay attention to. So first of all, this k doesn't really change at all as you're taking this summation. So in other words, you can take these terms, multiply them by k, and then add them all up together, or you can take these terms, add them all up together, and then take the end result and multiply that by k. In other words, we can factor the k out. So it's a little bit how we do this with parentheses. This is a term that is common for all, it's a factor that's common for all the terms in this summation, so we can just pull this out. All right, so that means we can take the k, put it here, and the next thing we can do is, well, this one changes as I runs from 0 to n. And this thing changes because, of course, the distance is going to depend on exactly which charge you're looking at. And then similarly, the unit vector is going to change. So these 3 we can't factor out, but this little q here, we absolutely can factor it out. So that's k times q. And now I'm regretting writing the k first. So I'm going to put q times k. And now I do the same thing. I'm going to write this. I'm going to say, okay, I'm going to let my index, run from 0 through n. And I just would like to know what that vector is. I could still call that little q I squared. But at some point you get a little tired of writing the little q, so oftentimes we will drop the q, except it's still important. And now you see that indeed there is a Coulomb force that you can determine for some arbitrary charge q. Once you've added all these terms together, all you need to do is multiply that end result by little q. And then you figure you've got your net force. So when people first saw this, they got really excited because they said, "Oh, you know what? I can just call this something else." And this thing I'm going to call the electric field. So by definition, the electric field. So we use the symbol E for electric field. And as you can tell that, once you have the electric field, you multiply it by Q, you get a force. So that means that the unit of the electric field is force, because this left-hand side here is force. Force, so units of force are newtons per Coulomb. There's another way to write this, but we haven't done the other unit yet. But this is the way that you could think about it. So in other words, you got some electric field. You want to know how many units of Newton, how many newtons are acting on it. Once you know the charge, you just take the electric field, multiply by the charge, get a number of units, newtons. In other words, same thing here. So you have an E, and then you could just say that is Q. I'm sorry, I'm mixing it up. So once we've done this, we can just say F is Q times E. All right, looks simple enough. This is still Coulomb's force law, except we factor out that charge under consideration. And the devil's going to be in the details of this electric field. So as you can tell, it mathematically looks the most complex. But once you've worked out what this term is, then afterwards what you're left with is multiplying by the charge under consideration, and then you got your force. All right. So a couple of tricky things here. It might seem that this electric field here is completely independent of little q, but it is not really, because this electric field is the field evaluated at the location of this charge. So even though the electric field is due to the n other charges, we still want to know what the electric field is at the location of this little q. So in other words, we should really write this as the electric field at some location r of q. So because the electric field is going to vary, because when we change the position of little q, this distance squared is going to change, and this unit vector is going to change. So this electric field here is going to depend on the location of that charge. So the electric field itself does not depend on the magnitude of that charge, but it does depend on the location where you're evaluating the electric field. Okay, so that's the tricky bit number one. Evaluate E at RQ, right? That's the first part. Tricky bit number two. All right, for three, come on, charges, there are two pairs. So in other words, if in this situation we have a Coulomb force that we would like to evaluate at the location of this charged object, we have one 2, 3, 4 pairs. So even though we have 5 charges, we have 4 pairs. In other words, there's going to be 4 terms in the summation. And you'll always get 1 term less than the total number of charges. This is something that is always confusing. So I'll do a couple of examples where it will become more clear. Another thing is, this is sometimes confusing. I do a lot of programming. I usually let my counters run from 0 to n, but where you stop before n, that's confusing to most physicists that do a lot of programming, even though I think that should not be a possibility. So let me just start that at 1. All right. So that's the concept of the electric field, right? So you want to know what the Coulomb force is on some kind of a charge under consideration. All you do is figure out what the field is at that location, then plop in your little q, and then you got your force. All right. Now, little q has a name. Little q is a test charge. So little q is a test charge. What do we mean by that? Well, 2 things. It's small and it's positive. So what we do when we figure out what the electric field is, usually what we'll do is we'll first assume that q is small. So in other words, when we place little q in the environment generated by all the other charges, we're assuming that nothing's going to change because this thing is small. The other thing we'll do is we'll assume that this thing is positive, because then you don't have to worry about all the other sign changes. This is not strictly necessary, because if you're being super consistent, you can do all of this with negative charges, but that's no way to live. All right, all your minus signs would work out. So this is the basic formalism for working with the electric field. So now let's see this thing in action. Number this page. All right, here we go. So we'll do the exact same problem that we had before. So we'll start with 1, 2, 3 charges. Okay. We want to know what the force is right here. But we're going to use the electric field instead of the Coulomb force law. And then afterwards, when we have the electric field at this location, we'll put this charge in. So in this scenario, we're going to call this little q. We're going to call this number 1, and we're going to call this number 2. Number 1, number 2. Okay, so now, according to our recipe, we can say, okay, you know what? The force is q times E. So if we want to know the force, we take q, multiply by E. Okay, and now we want to write E is going to be k times the sum. I is 1 through n q I over r I squared. You see I've dropped the little q. So let me not do that actually because it's confusing. Okay, so all of the information is going to be in these 3 terms. So we've got 2 terms. So in other words, we have a k because we have 2 charges. We have a q1 r hat q1, and I apologize, sometimes I reverse these for some reason. Okay, that's term number 1 plus q2 r a little q2 r squared q2, and this k multiplies the entire sum. So in other words, this thing goes in brackets. All right, now we need to know what this vector is, and also what the distance is. So let's put some kind of a coordinate system on here. So it's It's a one-dimensional problem. I'm just going to put the x-axis running in this direction. So using that, we get an R from Q1 R from Q to 1 so from 1 to Q goes from here to there, so that's in the x hat direction. And let's call this 1 meter because that's what we were doing before. So 1 meter. So this is x, and if you want to be really, really careful here, this thing is unitless because it's the unit vector, so we can just say x times 1 meter. Okay, so that vector is pointing in the plus x direction. R Q2 is pointing in the opposite direction, right? Because if we go from 2 to Q, we go to the left. So it's going to be minus x hat 1 meter. All right, so having established that, we can use this and then rewrite this. We apply that here. And now we have a Q1 x hat. I'm going to drop the 1 meter for now. The units. Okay, that's x1, 2 with a minus sign. All right, so we're adding, but this thing points to the left, so that's a minus sign. 1 squared is simplified as a little bit more. So it's k x hat Q1 minus Q2. All right, now finally we have the electric field. Woo, that's the electric field at the location where we're going to put little q. All right, so in other words, now that we have this F, we're going to take Q times E, evaluated at the location of Q, and that's the force on Q, so I'm being super verbose here. So that is just a K, a little q, an x hat, Q1 minus Q2. So we get the exact same force that we had before. And let me go back to my notes to show you that I'm not cheating you. All right, this is the one we did 2 days ago. You see, all I did is I factored out the x, and you'll see that we have this Q1 here. This one is now Q2 because we have renamed the central charge to little q, but you see the rest of the structure of this equation is completely identical. All right, now what we now want to do is not only would we like to figure out what happens when we place that little q somewhere in a very well-defined location, but what happens if we put it in some kind of an arbitrary location. So I'm going to take one step back and not talk about 3 charges, but we're going to talk about 2 charges, one of which is going to be a test charge. So that's going to save us a lot of the summations. All right, that's number 2. So we've got some big charge here. That's big charge, big Q. And now we would like to know, what is the electric field here, such that when I place little q here, I can figure out what the Coulomb force is. Now we know that the electric field here is going to be a function only of the only other charge in this project, in this situation, which would be that big Q. So in other words, that electric field is going to be K Q R squared r hat. In other words, this electric field is going to point in the r hat direction. And the r hat direction is out, right? Because we point always from that charged object. So the electric field points in this direction. So it looks like this. And this would be the r vector direction. And if, by the way, if of course Q is positive. So what we can now do is we can say, okay, so I know that that's the electric field in this location. I could actually, I could move this charge around, right? So I could say, okay, so what's my electric field here? And we would do the exact same thing. We would find some kind of a vector that joins this location under interest with the location of that charge Q. And we would find the electric field looks like this. So we could do that for all possible locations here. And every time you do that, you would find a vector pointing straight out from this one. So in other words, all those vectors together are going to look like a bunch of lines that are going to come out. So all these vectors pointing out. All right. So, and that is if, of course, we do this at fixed distance. But if you get closer, you can ask if the strength is going to change, but the direction does not change. So the next thing we do is we draw, instead of those vectors, we draw a, I'm running out of colors again. Okay, we draw, and I'm drawing this right next to it because I don't want to go over it. We draw these lines. And I'm not drawing it super symmetrical. And then on those lines, we'll put little arrows to indicate the direction of these lines. And when we draw these lines, we will say E field is tangential to these lines, and they are called electric field lines. So what do we mean by tangential? It means that once we have a configuration of what these things look like, we could just pick an arbitrary point here, say, hey, where's my electric field going to be? And we look at, hey, the electric field line is running in this direction. So therefore, the electric field here would also be pointing out. So we can go from electric field lines to electric field, and then we can go from electric field to Coulomb force. Once we have the location, we can plot the force down. So electric field lines. Now, drawing this in a slightly less complicated manner, less details. I'm going to draw the electric field. 1, 2, 3, 4, 5, 6. And let me indicate that that's the electric field. And let me indicate that this is the charge. And Q is greater than 0. So this diagram captures all the same information that we have here, except I'm not actually drawing the electric field. These are actually electric field lines, but oftentimes we will label it electric field, even though electric field and electric field line, not totally the same. So this is the situation for a positive charge. And now I'm gonna turn on the Nearpod and let you sketch the electric field lines when this is negative. So give me a second, turn the Nearpod on. So that's where Nearpod's going to be. And level it out a little bit.
What is the second one?
So again, the assignment is draw the electric field lines.
Is there a new code for this one? Because it's not working still.
Yeah, it looks like you all got it. So yes, it's going to look just like this, except of course, anytime where we had an electric field pointing out, the only thing that's going to change now is because all we did is change the sign of this. Our hat is still pointing in the same direction. So all we're doing is changing the sign of that electric field, which means that also all these electric field lines simply just reverse direction. So 1, 2, 3, 4, 6, and they're all going in. All right. Now that's the first thing that we can learn from electric fields and electric field lines. So the second thing we can learn is how strong is the electric field. Okay, so let me try to illustrate that. So we know that this electric field here is going to go like 1 over r squared. So in other words, if we get closer to this charged object, the electric field is going to go up. Goes up quite a lot, in fact. Now, that might not immediately be obvious to you, but you can actually tell that the electric field becomes stronger because as you're getting closer to this charged object, so are all the other electric field lines. So the geometric insight is that more electric field lines implies stronger electric field. Stronger electric field. So in other words, right now here, the distance between electric field lines is here. But as we're getting closer, so for instance here, we're getting closer, this distance is getting way closer. And then of course here, we get really close, the distance goes to 0. And when the distance goes to 0, that means the electric field diverges, right? Because if r goes to 0, this thing goes to infinity. So in other words, we've got electric field lines. We can make these drawings. From the direction, we can find what the, from the tangent to this thing, we can find the direction of the electric field. And from how close they are, we can figure out how strong the electric field is, with one caveat. It's not an absolute number, right? So if you go here and you say, well, I've got 2 electric field lines and they're within 1 meter, you can't just say that the field is 2 field lines per meter, because it doesn't work like that. Because in these diagrams, we'll sometimes draw them more separated than in other cases. So it'll give you a relative idea of where the field is stronger, but not necessarily what the absolute magnitude of the electric field is. So got electric field lines. We've got a way to get the electric field. Now, the next thing to do is figure out what happens with electric field lines when our problem becomes a little bit more interesting. So I'm going to draw a charged object here and a charged object here. And then we're going to call this Q2. And let's, for simplicity's sake, just assume that this thing is positive. But now this Q1, I'm going to make negative. So we want to know now, okay, what happens with the electric field here? Because we are trying to prepare a thought experiment where if we place a little test charge here, we want to know where it goes. And we also want to know how fast it's going to move, or in other words, how large the force is. So step one in that recipe is, what does the electric field look like? And therefore, what do the electric field lines look like? So if you have a hard time visualizing this situation, you can always go back, and in fact, I do this in my head all the time. You can always go back to this idea of placing a test charge. So I'm going to just do that. I'm just going to cheat a little bit, and I'm going to say, okay, so now I have a positive test charge. I'm going to put this here. Okay, what's going to happen? So this positively charged test charge is going to be repelled by this one, and it's going to be attracted by this one. So in other words, it's gonna get, Coulomb force that looks like this. Okay, all right. Now, if I go up here, let's say I want to know. Okay, so how about here? So if I'm right in the middle, so the distance here is the same as the distance here, then this charged object, because it's positive, it's going to repel this test charge. So it might repel it, but it would do so in a direction where this electric field would be pointing in this direction. And this one would be attracting it, and it would be attracting it in the direction of this vector that's joining the little test charge. And it's doing this. So in other words, if I add these two together, I'll find an electric field that looks like this. And due to symmetry, right? So wherever I am here on this line, if I'm exactly in the middle, I will always find electric field lines that are horizontal. But I'm going to draw them a little bit further apart now here, because of course the electric field is going to get smaller as I move further away, right? So here it's stronger, and it's going to wave out. All right. So that's in the middle. So that's what the electric field lines are going to be doing. And they're pointing in this direction. There we go. So that's what the electric field lines are doing. Now, what happens if you get closer? So it becomes a little harder to visualize because when you get somewhere in the middle, it might be a little hard to visualize exactly what the direction of that field would be. But there are two limiting cases that make it a little easier. So for instance, we know that if we get really, really close to this charged object and we place a test charge right here, the Coulomb force is going to be super dominated by whatever's going on here, and it's not really going to see the presence of this charged object there, because this electric field is going to be much bigger. So in other words, if we get really close to this object, therefore also the electric field should look just like the electric field of an isolated charged object. So in other words, these field lines, they should all be coming in nicely radially. And they're all pointing in. The same thing here. So if I'm really close here, the electric field is going to be pretty much a function of this charge on the right. And the electric field lines are pointing out. So now all we need to do is find some kind of a way to connect these field lines with these field lines with these field lines. So the first one is easy, so that we just connect this one. That's field line number one. Now, the next one, as long as we make sure that we exit perpendicular to the surface, we can then afterwards just give it a little bit of curvature. And see, I'm not very good at drawing these things, but yeah, we sort of end up where we're supposed to be. The same thing here with this one. All right. All right. Now, you can keep drawing this because there will be field lines that seem to be going out here. But these field lines will always be closed. So this direction, this direction, this direction. So even though they go off the paper, that's what that looks like. So what we have now done is we have figured out the electric field lines. For and this configuration has a very specific name. It's called a dipole. So dipole, di from the Greek for two. So it's got two poles, one pole here, one pole there. They're separated by some distance, and this one's positive and this one's negative. And if we do this properly, a dipole is when the charges are exactly equal, but only differ by a sign. All right, I'll pause the recording for a second and say, see if there's some. So first question, if it's the question is whether it's always 6 lines, it is not. This comes back to the comment I was making earlier, is that if you want to know what the electric field here is, you can tell relatively by how close these field lines are, but you cannot get the absolute strength, because depending on the drawing, we might decide to draw way more field lines. So it's not always going to be 6 lines; it could be 100,000. The R in this problem is always going to be the location of this point under interest. So R. Now, when we vary the location of the test charge, we vary this vector R. And because we vary this vector R, we also vary the location with respect to these two charged objects. So remind you again that the electric field is going to be K Q1 R 1 on 1 squared, K Q2 R2 hat R2 squared. So as we're varying the points here to see, okay, where is the electric field pointing, we're changing this, we're changing this, we're changing this, and we're changing this. And in this case, R is the vector that is pointing from the location of the charge to this point under interest. So that's what I was. That's why I was making such a big point about putting the little Q here in the very beginning, because that makes it very clear that this thing is going to vary. So even though we're not moving Q1, we're evaluating its effect at a location that we can change. All right. So that, let me pause the recording again. So we resume 7 minutes from now. All right, so that's 13:59. So now we have the configuration for a single charge. So we got the we know how to figure out the electric field lines when we have, you know, a couple of discrete charges, so charges that we can enumerate. We simply figure out how the electric field looks when you're very close to the charge. You try to figure out if there's some kind of a symmetric point somewhere in between, and then you can kind of sketch out what the electric field is going to do. That's not really super exact, but you can get a pretty good idea of what it looks like. So we have this charged object, and then the charges are spread out. And if we sit here on this line, we want to know what the electric field is. So in this location. All right. Now, if this was a discrete case, we would say, okay, the electric field here is going to be K times the sum over all the other charges of Qi R hat I R I squared. This is sum over I. So except now we can't do this. We need to actually translate this into an integral because we don't have that amount of time. So we're going to change this into an integral. So it's going to look very similar. It's going to look like a K. And then we'll have to do some kind of an integral. And then we have to integrate over position. Now, I'm going to call this. I'm going to call this dx. Somebody keeps unmuting their thing. Please don't do that. So, so we want to know what this thing looks like. Okay. So what we can do is we can write very symbolically. E is the integral over dE, where dE is the contribution to that total electric field due to some kind of a infinitesimal line segment that is dx. So we didn't really do anything here. We just said, okay, you know, instead of having a sum, we have an integral. The hard part is going to be, what does dE look like? So dE is going to be some d, some derivative of K Q R squared R hat. So when we want to take that, when we want to evaluate that, the only thing that's changing here is the this R squared term and this Q term. So in other words, we can take the K out, we can take the R hat out, Q, so we have to figure out what this thing looks like. Now, this can become really tricky very quickly. So what we usually do is, instead of actually varying the distance, because we're not actually changing position, we're varying the charge under consideration. So we're not going to do this, but we're actually going to do this, because we can take the derivative of any term, right? So the next one we can do is K Q R hat over R squared D Q. Okay, so what I did was the chain rule, right? I can take the derivative of this with respect to Q and with respect to R, except we're not going to actually physically move that point in space. We're going to change the charge under consideration. So Now we need to ask ourselves, okay, what is dq? So dq would be an infinitesimal element here that is there. dq would be contributing to that integral some kind of a dE that is given by this term. Now we're almost done. All we need to do is convert this into something that we can actually integrate, because this is a dq, but we're not integrating over dq. We have to integrate over x. So in other words, we need some kind of a way to convert the dq to a dx with something. So in other words, what's the relation between the charge, infinitesimal charge here under consideration, and that dx? Well, we know that if we calculate this derivative, dq dx, we get the density, because q is going to be the density times the length, dx. And the length, just take the derivative with x, does not change. So you just get lambda. So the thing that translates the dx to the dq is the following expression. Lambda times dx. Okay, and now we're home, because we have an electric field that is the integral over some d electric field, some infinitesimal electric field contribution. We know now that dE is this term. The only thing we didn't know yet was this dx term, but now we know how to write that in terms of x. So now we can go back all the way to this expression and we say, okay, finally, we have converted this to an integral. So it's going to be k. And now lambda dx. I'm going to write this in the x power squared. And now, as I'm changing the position under consideration, this distance here is going to be r squared. This r is going to be x. Okay. Now, out of these terms under the integral, the lambda doesn't actually change. In this case, the x hat doesn't change because it's a unit vector, and it doesn't change direction either because it's always pointing to the right. So I can actually change this. I can do this. And now I have an integral of dx over x squared. And now we need to figure out from where to where we're integrating. Well, I didn't actually say that. So for instance, let's call this the origin. And let's call this point A. Call this point B. So we're going to integrate x from A to B. In this case, x is going to the right. So we're going to have to keep track of a bunch of our signs, but should work all right. So we're going to go from A to B. All right, now we can execute the integral. Okay, lambda x hat. Oops, square. That's 1 over x with a minus sign. Beta A equals, oh, sorry, I need to do this here. Okay, lambda x hat All right, now here comes the tricky bit with this expression. So the question is, now hang on a second. Isn't the electric field in the plus x direction? And this is why I was telling you that the signs are a little bit tricky. So in the way I set up this problem, A is to the left of B. So in other words, on this axis, B in absolute values is a smaller number than A, right? In other words, if B is smaller than A, then 1 over B is bigger than A. So this term looks like it's negative because 1 over B is bigger than 1 over A, right? So that looks like it's negative, except A and B themselves are negative as well. So it actually works out. This thing will point in the plus x direction. All right, we can change this expression a little bit. So let me just go to this here. So I'm gonna repeat E, okay, lambda, x hat. All right, make this AB. And now A becomes the B, B becomes the A. So when all is done here, usually it's a good idea to make sure that all your signs are working correctly, and also you didn't drop any funny factors here. So we usually look at this expression and then we'll try to see if there's a limiting case that we can make sense of to double check our answer. So the first thing we can do is we could say, okay, you know what? If we take these points and we move them closer and closer and closer, while keeping that total charge constant, so these charges get more densely packed as you're pushing them closer. At some point, all that charge is going to accumulate and it's going to sit on that point there. And then if I did my math correctly, if I take that limit, then I should recover the electric field due to a charged object evaluated at this location. So that's the question. What is the limit where we have both A and B going to X of this expression? Now, the first thing is that you might be tempted to think that B minus A, if X is going to be the limit for both of these, you might be tempted to think that this thing goes to 0, except it doesn't, because as this thing goes to 0, lambda goes to infinity, because the charge density goes to infinity. So before we can take this limit, we need to reconcile this lambda's changing behavior with this B minus A changing behavior. So the thing that stays constant is the total charge. And the total charge, because we know that total charge is lambda times the length, and the length is this term. Except it's got a funny sign. All right. So in other words, before we can substitute this in here, we have to do K lambda, K Q, that's lambda times L, right? X hat over AB. Right, so the lambda, let me draw that out. The lambda here those things together form Q, and the Q stays the same. And now we're going to let both A and B go to X. So we end up with K Q X hat over X squared. And that looks correct, right? It looks exactly like the Coulomb, it looks exactly like the electric field due to a single charge, right? So there's a Q, there's a unit vector that in this case is x hat, and then there's x squared. So this expression makes sense. It's the electric field of a point charge. So we know that our math most likely is not messed up. All right, so the hardest part about this is this part, the first part, figure out how to get the dq to relate to the charge distribution under consideration. That's the first thing. And then the second thing is, okay, once you've done that, how do all these things change when we consider different parts of the line? So for instance, what happens when this is not a one-dimensional problem, but it is a two-dimensional problem? All right, so we take the exact same configuration. So we have a line. Let's pick the origin here, and let's go from minus L over 2 to L over 2. So the total length is L. And for simplicity, I'm gonna sit right here, and I want to know what the electric field is here. And I want to do that by executing the exact same recipe, except now I need to be really careful. My my DEs and my R vectors and everything, they're going to look a little different, but it's still one-dimensionally. It's still a single variable for the integral because the object is just a thin charge line. So let's call this thing positive. And the first thing is that we recognize that we need to do some kind of an integral. The second thing we need to recognize is what that DE is. So the DE is going to look very similar to what we had before. So DE, let me pull it up for reference. So it's going to look like this term. So it's going to be K R hat over R squared dQ. So I haven't done anything. I've just put in that, you know, it changes with 1 over R squared, but I need to pay attention to this R hat now. And now, in order to change this to something we can actually integrate, we need to write this dq as a dx, and we do the same thing again. We say dq is lambda times dx. So in other words, we get the R hat, R squared, lambda dx. Now this is something we can work with, right? This is an x we can integrate over. We can set up, you know, our integral. We were going to go from minus L over 2 to L over 2. Now we just need to put the details in for this one. Now this is where it becomes tricky. This is where we need to put in details not only for this R squared, but also for this R vector. Because, let me draw that for you. Some kind of a segment here under consideration here, we're going to call this dx. This dx is going to give an infinitesimal charge dq, and that thing is going to generate an electric field at this point in a direction that is joining this point under consideration and the other point under consideration. So this vector dE points to the right. Now, as I'm going to change this point x as we're integrating over the length, not only is the distance here going to change, also this point is going to change angle, right? Because as I'm moving this thing, so like this, the direction of this electric field is going to change. So before, when I was integrating, I didn't really need to pay attention to what this unit vector was doing, except in this case, I do, because the length is not changing, but the direction is. So that's where one of the tricky parts sits in this problem. So let's call this height h. And let's set it up. So in this case, this is the r vector. The r vector points from this point to there. So if we now set up a coordinate system, so let's call x, y, r vector is going to have an x component and a y component. So let's put in the details. And I'm going to do this with Nearpod again. And I'm going to let you figure out what that is. So let me draw a little box and put that in Nearpod. Give me a second. And let me put the code on again, in case. So again, the assignment is, what's this? So here's the crucial insight. This R vector is sitting in the XY coordinate system, and it's pointing up and to the right. And you can draw a little right angle triangle here, where in this situation, the vertical component is the rise of this triangle, and the horizontal component is the base. So in other words, this is H and it's X, except we need to talk about what X is. So we've got an X here, and now we have an R vector. We can calculate the magnitude and everything, and then we can integrate it. Except this base here does not have length X, because to the left of this point, X is a negative number. So in other words, this thing needs to be minus X, right? Because when X is to the left, the vector is pointing to the right. So in other words, X is negative, the contribution to the electric field is positive. So we need an inversion here. There's just no way around it. Now, fortunately, if you miss this sign here, things will still work out, because after all this discussion about where the minuses go, turns out this thing is going to evaluate to 0, but only in this highly symmetric case. So be super careful. But now that we have this R vector, we can integrate. So all we need to do is plug this in here. So there are two ways to do this. The first is to convert this to an R hat and an R vector, such that you can plug those in here, and then execute your integral. Except I find it a little tedious when it's in this form. So for cases like this, I usually rewrite this, and I take a K R vector lambda dx over R cubed. Okay, so here's the tricky part. That's square cubed. And that is because I went from here to there. All right, now. Okay. Now we are almost done. We just need to put in all the details. So R as a vector has these components, so minus X and H, and the length is, Pythagoras, X squared plus H squared. And now you see that all that discussion about sine of X doesn't really matter as far as R vector is concerned. So we can take that and we can put that in here. And now the R vector, we're going to use these. So we have integral K lambda R vector over R cubed. Now, first I'm going to write down the R cubed. So X squared plus H squared cubed. I'm reversing my order of the powers, but that's perfectly okay. Okay, now I gotta write that R vector. So R vector minus X, H, finally, we're still integrating over X. So there's your dx. So that's the electric field. We integrate from L over 2, from left to right. And if we just execute this integral, we'll get a we'll get our answer. Now, first things first. What we have here is even though it's a single integral, it's going to give you an expression for the x component, and it's going to give you an expression for the y component. And we can actually integrate those separately, because this is actually minus x hat plus h times y hat. So if we write that in this term, instead of the vector in vector notation, we write this in unit vector notation. We have a product of something that we're integrating with a term in parentheses that is a sum of two terms. In other words, we can split that into two integrals. So we're going to write that as two integrals. We're going to write same integral, okay, lambda. And now I'm going to write this a little bit more economical, 3/2. And now the first term is going to be this one. So it's going to be minus x hat dx. All right, plus the integral, same thing, except now I only want to know what the y component is doing. So that's a minus. Times h times y hat dx. Okay, so all I did was split this out in two terms. This one you can integrate. This one's not too hard to evaluate if you really want to execute the integral, except you don't really need to, because you will see that this term that we're integrating here, this function, it's odd. If we change the sign of x, this term changes sign. And if you're integrating from one point to the left to the exact same point, but on the right of something that is odd, when you integrate that, the outcome is 0. So in other words, the x hat component evaluates exactly to 0. What does that mean for the electric field? The electric field will finally only have a y component. And that actually makes a lot of sense, because if you look here, for any point here on the left where the electric field is pointing to the right, we have a point exactly on the opposite side that is to the right, pointing to the left, with the exact same x component except pointing in the opposite direction. So because we picked this point exactly over the center, that holds for all the points on the left here. And therefore, because all the points on the left have an equal but opposite point on the right, all of these x components, they're always going to cancel. So the final electric field is going to only point in the y direction. That's one way to look at it. Say, okay, you know what? Due to symmetry, there's always something on the left that is equal and opposite, has the equal and opposite x component on the right from a point on the right. And therefore, due to symmetry, this thing is going to point straight up. Another way to look at it is say, well, you know, if you actually execute the integral, this integral is odd. And sorry, this term is odd, and you're integrating from equal bounds left to right. Therefore, because it's an odd integral, that must evaluate to 0. The third way to look at it is use counterexample. So say, okay, you know what? If we assume that this thing has an x component, so for instance, I'm going to draw this like this here. So let's say it has some kind of an x component. Now, because of symmetry, I should be able to take this wire and rotate it. So I'm going to bring this out, bring that out. So all I'm doing is rotating the wire. And if I'm doing that, this thing must also rotate and then end up on this side. But when you rotate this wire around this axis here, you haven't really changed the configuration because of symmetry. So in other words, if it has an x component, that x component would change sign. And the only way that you can have an x component that changes sign and stays the same is if the x component is 0. Right? So because you're not allowed to do this, and then have it point the opposite direction, because symmetry dictates that it cannot have a preference for pointing to the right versus pointing to the left, because this thing is the same if you turn it over. All right, so 3 ways. After all that, we have this integral, and this integral is kind of nasty, and this is one of those that I usually look up. So there's a k, there's a lambda, there's an h, there's a y hat, and finally the integral is from dx x squared plus h squared 3/2, and you go from minus L over 2 to L over 2. Okay, this is an integral that you would solve using trig substitution. And I promise you, if one of those integrals shows up on the midterm or final, I'll give you the outcome. Because this is just going to be something that depends on h, and it's going to be some kind of a number, and then times L. And that's our final electric field. So we are done. That's the electric field. So we know it's pointing straight up because it has only a y component. We know how it depends on length because we can just integrate this thing. And then we are done. There are still some tricks that we can use to rescale this integral. I don't want to get into it, but for instance, oftentimes you can take the length dependence out or factor the h out, so you can get something that that only depends on something and h or something and L. So usually you don't need to keep this a function of both L and h. That usually takes a little bit of fiddling, but it is totally doable, but it is not necessary. All right. So so finally, so we've done this for two-dimensional situations of one-dimensional charge configurations. We can do some more examples if you want, but in general, the recipe, because we're kind of at the end of class, the recipe for one-dimensional charged objects means that we have some lambda and a dl, and then depending on how we set up the trig substitution, yes, was a question if that was substituted by a tangent, yes. And I think I have it somewhere in the book. So for one-dimensionally charged object, we use a linear charge density lambda, and we integrate over the length, and then we have some dq, and then we need to have an electric field that is infinitesimal, that is just k lambda dl over r squared, and then there's an r hat here. So all we need to do is figure out, okay, what's that variable that we're integrating over? What does r hat do? And what does r squared do? And then once we have those details plugged in, we have a dE, and we can integrate and get the electric field. In 2D, we have, we could do some next class. In 2D, we have a charge that's spread out over a surface. So sigma is actually surface charge density. So the units of lambda here are coulombs per meter, and the units of sigma here are coulombs per meter squared. And then the rest goes the same. We just have a dE, we have a k, we have a lambda, sorry, sigma dA r squared r hat. And then in 3D, for three-dimensional objects, we have a rho, and we integrate over volume. And now your dE is k rho dV r squared r hat. And the units of rho, density, coulombs per cubic meter. And the rest is just putting in the details. We'll do a couple of those examples in next class on Thursday. But before we do that, I want to actually try to figure out where we are. I usually make these diagrams, I usually make these diagrams as soon as we've introduced a new concept. And throughout class, I'll try to keep coming back to this diagram. I call it a concept map. I believe that's the right term, but don't blame me if it's not true. So we've got a couple of things. We have a we have a Coulomb force. We have an F sub c. We have charges, right? So we've got a Q. We've got electric fields, and that's it, right? So these are the basic objects that we've talked about so far. So started with the Coulomb force law. We just had two charges that were interacting through this Coulomb force. And then we teased it apart and we said, okay, you know what? We can say this electric field due to this one charge is exerting a force on the charge if you put it in. So in other words, our diagram right now looks super straightforward. We have some kind of a charged object. That charge object creates an electric field. And then that electric field, if we place another charged object in it, is going to feel a force that is proportional to that electric field. So in other words, the Coulomb force law is the combination of this and this. So from Q to E just means that you integrate, right? So we know how to do that now. I'm gonna scribble it here. So we just do a dE is, so it's a linear term, depends linearly on the charge. All we need to do is execute that integral, and then we get an electric field. Once we have the electric field, we can place another charged object in, and then we get this force. In other words, this path in the concept map, going from here to here to here, and then ending up there, is the Coulomb force law. So in other words, if you want to read this, diagram, you want to say, okay, so how do I know from this diagram that likes repel? Well, it's all in here, because Q is going to create an electric field that points away from Q because of the way that we integrate. And that means that if we put a positive charged object and here and a positive charged object there, then the force is going to be pointing away from this object. In other words, if they're both positive, they're repelled. Or if you want to look at it differently, if we make this one negative, then this would still be pointing away from this object. So the electric field would be pointing away from Q. But now if we make little q negative, that means the force is pointing in the opposite direction to the electric field. So it's pointing towards the charge. So this path not only shows you the Coulomb force law, but you can also work out what the nature of the interaction is. So it's all in here. This path is still that same expression, except we kind of teased it apart, and now it's a little bit easier to work with. Even though you might be tempted to think that it's a simple equation, why don't we just keep doing this? Well, it turns out there are really many ways in which you can calculate an electric field in a way simpler method. So let me finish by saying that the process that we were just doing is called direct integration. So direct integration, just take some charge configuration, figure out where the vectors are, execute your integral. For instance, with computers, that's super easy to do. The thing we'll do, I think we'll get to it on Thursday, is we'll try to figure out an alternative to direct integration that sometimes works. Situations of super high symmetry, you can probably get away with not having to do direct integration. So direct integration, it's usually more work, but it's guaranteed to work. Whereas the thing that we'll develop on Thursday will not. So with that, I'll take any final questions. So if there are no more questions, I'm going to pause this. In fact, I will actually end the thing. So this recording is going to be separate. And then I'll sign into this meeting in about 7 minutes again for office hours. Thank you, everybody.